bit about schema management in NoSQL stores.
Yes.
Okay.
Yep. So, thank you for the invitation. Okay, ready. I will talk about NoSQL Schema management and big data migration in the cloud. The work is a collaboration with Michael Tetke from University of Rostock and Stephanie Schatzinger from Uta Regensburg. We are working together in a DFG project as a German research foundation. The talk will be divided into two parts. After a short motivation, I will talk about NoSQL schema management and NoSQL schema evolution management, and in the second part about big data migration in the cloud. So the motivation comes from real-life project, from experience, from application developers in the context of agile development. Agile development is very popular nowadays and comes with frequent schema changes. We often see weekly or up to daily schema changes in such projects. And of course, schema flexible database, NoSQL databases are very popular because you can push your new release and without any schema changes in the underlying database, and it's easy to use. So everything is fine. No, not everything is fine, because the responsibility for the schema management is from the database delegated to the application. The application has now to deal with, the application has a schema. You have your classes, you have your the structure of your application, and when pushing a new version with a different schema, you now face in the productive database different kinds of data, you get heterogeneous data. The question is how to deal in a new application version with the old data. And state of the art, meaning in productive environments, is writing migration scripts in the application code. This is expensive and of course error-prone. So as a database community, we don't think that's the right way. We think that's possible, that's important to support optional schema management for NoSQL databases. Of course, optional because we don't want to lose the flexibility. If you don't need schema for your application, for your environment, then it's okay. But we want to have an optional schema management for NoSQL database systems. We started with this research some years ago, and there were no products supporting schema management for NoSQL databases at all. And some reviewer gave us feedback, schema management for schema flexible databases, really? Yes, he said, really? And in the last few years, also some tools emerged. Some tools which support different databases, call it multi-data store tools, like Calculate and Erwin. I think some of you know Erwin. Erwin is a well-established data modeling tool for relational databases, and they now broaden their scope to NoSQL databases. And Calculate is an interesting company, a new company emerged in the market, which supports a lot of NoSQL database systems. And we have some, a lot of, sorry, it's not my presenter, I forget my presenter, thanks for Felix. Some single data store tools like StudioSQT for MongoDB, and MongoDB itself has now some schema supporting features. When speaking about NoSQL schema management, we have two approaches: forward engineering and reverse engineering. What does it mean? Forward engineering means we are able to create a schema, like we know it from traditional relational database management. We are able to define our structure with arrays and the structured object and so on, and also the relationship between the entities or classes. And as output, for instance, when using Hackulate, you can create a JSON schema as a universal format or proprietary schema formats for some proprietary schema extension modules for different NoSQL database systems. But this forward engineering, this greenfield approach, is not the typical use case in a real-life project, so the reverse engineering is a more interesting one. It's typical that the application developer starts without schema management and then face the challenge I talked about in the beginning. So what does this tools offer? We have two functionalities, schema overview and data exploration identified. Schema overview means that you can, these tools analyze your data and all detect all occurring attributes or properties. And the second functionality is data exploration. That means that the data or sample of the data is analyzed and information about the distribution of the data types or the distribution of the data. For instance, in this example, one attribute occurs in 25% of the data and another one in 50%. Okay, the small set, you have these 150 and 25% numbers. But the question is this the solution to the problem mentioned in the beginning? We can now define schemas, we can validate data against the schema, we can extract schema overview and explore the data, but we are still not able to deal with the heterogeneous data because we do not know anything about the history of the schema, about what is the current schema, how to migrate the data into the current schema. And therefore we need another approach. We propose that we do not only need schema management for NoSQL database systems, but schema evolution management. And for schema evolution management, we proposed a schema evolution language. The language contains single-type operations and multi-type operations. Single-type operations are simple operations which refer to only one entity type, and the more interesting operations are these multi-type operations. Multi-type operations are very important when restructuring your schema, your classes. For instance, the move operation for refactoring to copy a property that's important in the context of NoSQL database systems, because due to performance reason or due to the lack of a join operation, you often need to denormalize your data and accept redundancy. And the question is how to get these operations. Of course, we again have these two approaches: the top-down approach. The developer can specify these operations, but again, this is not the real-life use case, because they do not want to change their classes and then specify the schema evolution operations. The more interesting approach again is a bottom-up approach. We proposed, we call it advanced reverse engineering approach, where we extract the schema versions from the data. Let's have a look at an example from marine biology, of course, because Michael is located in Rostock on the Baltic Sea. We have two different kinds of data, two entity types. One are species, and the other one are protocols which describe observation of species. And as you can see, over time the structure of the data changed. We added an attribute called category, was a species. And later on, this category attribute was renamed to worms, or verbs, World Register of Marine Species. And later on, we decided to performance reason to copy this worms attribute to the protocols entity type. And now we have these heterogeneous data within our database, and the question is how to extract schema versions and schema evolution operations to migrate the data in the current version later on. So in our approach, we build schema graphs from this data and derive schema evolution operations from this graphs. Some operations are easily to derive, like an add operation, but when deriving these operations, they may occur ambiguities. Because, for instance, we cannot automatically resolve whether this is a rename operation, rename species category to worms, or whether it was a sequence of two operations, delete the category attribute and add the worms attribute. And the same challenge deals for copy operations or move operations and the corresponding join condition. We implemented this approach in our schema management component Darwin. I will come back to Darwin some slides later. And we decided to, in the first version, we decided to choose the ambiguities manually by the developer or database administrator. We present the decisions that have to be executed, and then you can choose the right join condition, for instance, and proceed. But we have also proposed an automated solution where we analyze not only the structure but the data and derive inclusion dependency. And based on this inclusion dependencies, we are able to propose to propose which will the operation and suggest meaningful join conditions. So in the end, we get not only a schema overview like the other tools, but schema history with the different schema versions and the schema evolution operations between these versions. And based on these schema evolution operations, we are later able to migrate the data automatically. That will be the second part of my talk. So we also implemented in our schema management middleware called Darwin. Darwin supports the whole life cycle. We are able to define a schema or to extract the schema from existing data. We can change the schema again by declaration or by an incremental extraction. Besides the initial extraction, we also support an incremental extraction when new data is arrived, and we are able to migrate the legacy data. The architecture of the system is so that we support different kinds of NoSQL database systems, document stores, white column stores, and at the moment we are integrating multi-model databases, ArungoDB and OrientDB, and graph databases, namely Neo4j. So, to finish the first part of my talk, I hope I have introduced that it's necessary to support schema management as an optional feature for NoSQL databases. And besides the basic features, we propose an advanced approach for schema version extraction. It's not supported in products yet. It's, as far as I know, it's only supported by our schema management system and by research work in the group about around Jesus Garcia Molina in Spain. They have a similar approach. So for some further reading, I have some papers here. So are there any questions to the first part of my talk? Schema management, schema management.
So maybe one question. So I do remember quite old word from Bernstein, I believe, about model management operators. I don't know if your word also relate to that. Not at all.
Sorry, I didn't understand.
Okay, so there has been some work in the field of model management,
Yeah.
database models.
Yeah.
Have you also been considering that?
Yes, of course, the schema management is in relational database systems. It has a long tradition in the database community, and of course, we also adapted this work. But the new challenge is that you are able in NoSQL database systems to put this data in the database without any changes in the database, and so the relational databases are more restricted. Okay, then the next part is we are still the heterogeneous data in the database. And now the question is how to migrate the data and how to migrate the data efficiently, because we're talking about big data and we're talking about databases in the cloud. Maybe in the cloud. The database can be on premise or in the cloud. And so we want to support data migration as a safe process based on the extracted or defined schema evolution operations, not with these error-prone migration skills. So let's have a look first at basic strategies of data migration. The first approach is eager migration, where after each introduction of a new schema version, the data is migrated. Of course, this is advantage of this approach is that all entities are in the current version. We have low latency because nothing has to be done when reading the data. But of course, this is the approach with the highest cost, and especially in the cloud environment, you are migrating all your data, so it's very expensive because all your data maybe that is not used for 10 years, but you migrate it because you have a known version. Can't be the solution for big data. The approach on the other hand is lazy migration, where you only migrate entities when they are accessed, not during a schema evolution or something like this, or only when the data is accessed. So of course it is the cheapest approach in terms of costs, but you have a significant increased latency because you have to migrate the entity when reading, and depending on the operation, maybe if we have a copy or move operation, there may be other connected entities that have to be migrated. That can be very expensive in terms of time. So we have a trade-off between the migration costs and the latency. And the question is there any approach in the middle which provides us a good compromise between migration costs and latency? And we've done some work in this area, how to reduce costs of data migration. The first approach is to optimize data migration operations. We proposed some work to composite migration chains of evolution operations. This will not be the part of my talk today, but if you are interested in this topic, we can discuss this later. And the other approach is to develop proactive migration approaches or hybrid migration approaches, like incremental migration or the more interesting one, predictive migration. Incremental migration means that you do not migrate the entities each time when a new version occurred, but at some times the entities are migrated. So you have cheaper costs, but we are still migrating all data, and all data again, all data that is not in use. So it's better than eager migration, but it's not such a good solution. So the most interesting one is predictive migration, based on a forecast function. Entities that are accessed in the future will be migrated predictive. And if you have a good prediction function, then we decrease the average latency significantly. And also we reduce the cost, of course, because we only migrate the entities which are needed. So hopefully, predictive migration will provide us a compromise between latency and migration. So we implemented predictive migration, or two different approaches for predictive migration, and our vision, our goal is to provide a migration advisor which supports the application developer to choose the right migration strategy depending on their application environment, their infrastructure environment. So we have a lot of input parameters. Of course, we have the characteristics of the data set, the size of the data, the whole size of the data, the size of the individual data pieces, the cardinality, the connectivity between the entities, and so on. We have, like always in databases, the data access pattern, whether we have a typical OLAP or OLTP data access behavior. We have our schema evolution, how often schema evolution operations occur. Do we face mostly single type operations or the multi-type operation? And we have the characteristics of the DBMS, like Heiko and Felix already told, the NoSQL DBMS has very different characteristics regarding their read and write performance, and also questions about how is the data distributed, how is the replication factor, and so on and so on. And last but not least, if we have a database in the cloud, we are talking about the cloud pricing model, which are very different from provider to provider. And we have the question, how are the data migration operations implemented and optimized. As a first approach, we implemented Recast, migration forecasting tool, which is built on top of Darwin. The input parameters are, as I already told, the characteristics of the data set, data access pattern, schema evolution, and characteristics of the DBMS and cloud pricing. And based on these input parameters, Recast calculates the migration costs and the data access latency. And inside Recast we have a workload simulator, a cost calculator, and then latency profiler. And the user can specify these parameters interactively during a GUI, initial number of entities, data codes, data access pattern, and so on. We have a lot of advanced settings. If you're interested in have a backup slide. And as result, we get the first row, we get the migration costs. The migration costs on release, that means when a new schema evolution, new schema version is introduced, and depending on the data migration strategy, this results in costs. And the migration costs on read, that means costs that occur when an entity is accessed and is migrated, or maybe other entities are migrated as consequence of this read tool. And the migration costs cumulated are the sum of these both costs. And as you can see, the eager migration has the highest cost, and we implemented two predictive, besides lazy and incremental migration, we implemented two predictive approaches. One is called predictive, and one is called predicamental. We are looking for a better name. The idea is that we not only migrate the predicted data, but at some times when the backlog of schema evolution operations is very long, when we have we would have high costs in case of a read, then we decide to expand the prediction set and migrate a higher number of entities. And you can see this at, okay, here you can see this is at the point where we decided to migrate, to expand the prediction set, and then the cost of predicamental migration are higher than for predictive, but as benefit we get lower latency for this predicamental approach. And you see the latency per entity access, and of course the lazy has the highest, or the highest latency rate, and the eager migration the lowest. And now the question is for the project to decide what is more important for me. Will I spend the money for the eager migration, or it's more important to have a good latency, or will I accept lower latency and save money? And we also calculate the migration depth. That means that are the costs that would have to be invested in order to migrate all legacy entities to a homogeneous database. For instance, if you have the need to migrate from one provider to another provider, or if you want to decrease the latency and decide to migrate all your entities, then these are the migration depth. Okay, this is a demo we will present in 2 weeks at the SIGMOD in Amsterdam. So, already finished because you didn't ask so much. Norbert told me not too much slides, they always discuss.
Too much slides.
So I hope I gave you the motivation for schema evolution management in NoSQL databases, and I presented you some approaches for schema evolution management and big data migration for NoSQL databases. Research work is we just submitted a paper for evolution management in multimodal databases and polystores. So we can see connection to the previous talk, because it's of course an interesting use case when we have different data models and data is stored, as Heiko told. Some data is stored in all data stores, and some data is stored only in one data store, or maybe linked or connected to another data store. And so the question of schema evolution becomes new challenges. And the second main topic at the moment is that we want to craft a dedicated NoSQL schema evolution and data migration benchmark. That's a real challenge, because there's no common understanding in the NoSQL community up to now about NoSQL use cases, NoSQL data access pattern, and what is the appropriate benchmark. It's still an open question in the NoSQL community. And we not only want to have NoSQL data and databases, but schema evolution. The next question is, what is a typical schema evolution behavior? At the moment we are analyzing a GitHub project, how their schema evolved to find a foundation for our work. And as I already talked, the final goal is to design and develop a data migration advisor, and we have to develop a host function host functions to support this decision about an appropriate data migration strategy. And the whole work is embedded in the DFE project, as I told in the beginning, together with Michael Klemke from University of Rostock and Stefan Schatzinger from OTH.
Okay,
So,
thank
I'm
you.
finished.
Questions? Yeah.
So, you said a few things about it, but I want to ask again, to what extent does it, what you do especially in schema evolution, depend on the type of a NoSQL system? Whether or not it is yeah.
Say loud. Speak out.
I didn't
How does what you do in schema evolution depend on the type of NoSQL system you put?
Okay.
Geht doch.
Whether it is a white column store or QL store or something.
Our approach fits very well for document store, white column stores. At the moment we are discussing about extensions for graph data store because there are some features, for instance, changing a relationship to a node, which are not covered by our schema evolution language. But in my opinion, the really challenge is that the behavior of these systems is so different. That's not a question of the data model, that's a question of the data stores. That some are optimized for read, some are optimized for write. So the results, das sind zwar the results for MongoDB, but the results for other data stores may be completely different because of the different properties of the data store. That's the challenge for the environment.
Other questions? So let me ask another question. How often is it the case that there is a schema evolution necessary?
It's a difficult question. We read a paper from Yahoo where they talked about weekly schema changes, and in case of agile development, weekly changes are typically, and we try to analyze this GitHub project, and often you see in the beginning of a project a lot of schema changes, and we have phases where are not so many changes, and maybe later on again a lot of changes because you have serious refactoring.
And what are the most used evolution operations?
Often I use add and rename, and then you have phases where you use a split and merge because you have a complete restructuring, or it would mapped to the move operation in our use case. But this is still an open question, and we are still try to analyze and publish metrics and the results of this. The analyzing of this, or to answer this question, is also part of this project, but not yet done.
Thank you. Other questions? Yeah.
The results that we have seen for the different cost functions, are there in this use case from the Marina Institute, or where does the data come from?
Okay, this is the application is another use case with 3 entity types which are connected, and it's possible to configure. That's dangerous. We have here the advanced settings, and we can configure the cardinality because it has a big influence between the 3 entity types. It's a model with player, mission, and places, but it's a very simple scenario, but it can be adapted to the individual use case.
So the 16 changes that we have seen, is that the simulation, or is it coming really from the use case itself?
No, that's random, because every run generates a new, not a fixed application scenario, but it's depending on here you can change a lot of parameters, and then it's calculated each time. It's not a fixed scenario.
Okay. So that's it. Thanks again to the speaker.